Okay, so we're going to have a look at a video on AS chemistry, although it's also applicable to any level of chemistry at school. And we're going to look at today at intermolecular forces. So we'll just do a sort of a brief overview of intermolecular forces before we actually get stuck into the sort of the more detailed aspects of it. So first of all, intermolecular forces will affect the physical properties of elements. So we're veering away here. We're not involving chemical properties. So in other words, how these things actually react with oxygen or acids or water or things like that. We're looking at physical properties, and essentially at A level in chemistry, we're looking at how these affect their melting point and their boiling point, and also how they affect their solubility. Those are the sort of things that we need to be able to predict from the intermolecular forces and to explain why they have high or low solubility or high or low melting or boiling point. So we have three main types, okay? They are, first of all, van der Waals forces, also referred to as London dispersion forces, and as temporary dipoles also. So you've got a bit of terminology there. You need to be able to sort of realise that certainly that one and that one, not so much the London dispersion forces, although dispersion forces may be called on occasion. Then you have permanent dipole attractions, okay, and then you have hydrogen bonds. We're going to look at all three of these, and I've listed them in this order because if we compare them like for like with molecules of the same or similar sizes, the van der Waals tend to be the weakest and the hydrogen bonds the strongest. So what we're going to look at is we're going to look at what causes these forces and how we can predict whether some molecules and structures will have weak or strong van der Waals forces, and explain relative melting and boiling points and solubility because of their different intermolecular forces in them. This should be stressed that intermolecular forces only control the physical properties of, and this is important, of simple covalent molecules. So it's important that you're able to identify your simple covalent structures. So you're talking about things like water, carbon dioxide, nitrogen, all the halogens, all the group O, and the noble gases. Okay, so in other words, not things that are ionic, not things that are metallic, okay, and certainly not things which are, of course, giant covalent. So things like graphite, diamond, silicon dioxide would not. They are, and we'll look at a wee graph later on where we sort of compare melting and boiling points of things where we're breaking covalent bonds or when we're breaking intermolecular forces. Okay, so the other thing you might want to consider is that when we talk about intermolecular forces, so hydrogen bonds are the strongest. When we talk about hydrogen bonds being the strongest, relative to the strength of ionic covalent metallic bonds, they are still, even as the strongest intermolecular force, they're still weak relative to those particular substances or those particular bonds. Right, okay, so we'll start here. We'll have a look at what van der Waals forces are, what controls them, and how they affect the physical properties of particular substances. So, van der Waals forces. Right, so they are essentially affected by the number of electrons within a molecule. So if I was to take a really simple example, if we were to go to group O in the periodic table, the noble gases, and we were to plot boiling points of those noble gases, okay, we would end up with a graph, maybe not exactly like that, but pretty similar to that. Okay, so that's the boiling point, okay, in degrees C, and that is the, just as we go across the, or down the group, okay. So that's fine. We need to be able to explain this trend and why this trend is as it is. Right, well, let's have a look at so these are all monoatomic, so in other words, neon just exists as a little atom of neon on its own. Well, if I want to boil it, what do I need to do? Well, obviously, let's imagine I have liquid neon to begin with. Well, if they're liquid, there must be some sort of, and you remember this from key stage 3 states of matter, there must be some sort of attraction between the two. And the more energy that is needed to overcome that attraction, the higher that the boiling point of that particular thing must be. So what we're saying is, I'm going to take neon, it is a liquid, and I'm simply going to turn it into neon as a gas. And you can see why that's physical properties, because that's a physical change, liquid to gas. There's no chemical change. I still have neon with the same number of protons, neutrons and electrons. I've just turned it into a gas. If I was then to take maybe krypton, okay, I'm drawing these a bit bigger and you'll see why that is in a little second. So this is krypton, and I'm doing exactly the same thing. I'm turning krypton and I'm boiling it, okay, and what I'm saying by this graph, okay, if krypton is there, is that the energy needed to separate these molecules as a liquid, krypton, is greater than the energy needed up here to separate the neon molecules into a gas. So the question we need to ask ourselves, well, why is that? Right, well, let's imagine to take any of these, it doesn't matter. Let's take one of them, and there's the nucleus. And if we imagine the electrons at any one particular femtosecond, an extraordinarily small amount of time, let's say, and the electrons are constantly on the move, so they may, in fact, distribute themselves to a greater proportion at one end of the molecule. Now, what does that mean in terms of the molecule? Well, that means that the electrons, because they're the mobile part of the molecule, okay, they're constantly on the move, that the negative charge of the molecule is now more distributed towards the end that my pen is on now. Now that means that this end becomes negative. Now how do we show that? Because it hasn't lost or gained electrons like in ionic bonding, so we show it as a delta negative. Now that means this other end must be delta positive. And that means in chemistry just a little bit positive and a little bit negative. Now let's line up another one of these molecules beside it here. Let's say another one the similar size. Okay. Now what will it do to it? Well, this is the negative end, and this has got electrons in it, so it will repel the electron cloud in this one in that direction. Okay. So if we redraw this, and I'll do my best with my limited artistic skills here. Okay. That means that the negative electrons are repelled down that end, making that delta negative and making this end delta positive. Now, suddenly, which we didn't have here, we have got an attraction. And this attraction caused by the fluctuation in the electron cloud is what we're studying at the minute. And I'll just write VDW, that is our van der Waals force. Okay? Now, then we need to ask ourselves, well, the van der Waals force in neon must be weaker than the van der Waals force in krypton. So why is that, and how do we explain that? Well, in neon we have fewer electrons than we've got in krypton. If you look in your periodic table, and it's probably a good idea to have a periodic table by your side, you'll see there are 10 electrons in neon, whereas in krypton we have 36 electrons. So there's a much bigger electron cloud. Which means then I can, in krypton, get a much bigger, if we call that the delta positive, delta negative, that will be delta negative and delta positive. And if we sort of drew those relative to what we would get in neon, we're going to get a much smaller delta negative and delta positive. So therefore, the size of the temporary dipoles here, okay, a dipole meaning a negative end and a positive end, okay, in neon is much smaller than that of krypton. So therefore, as we increase the number of electrons in something, we increase the van der Waals forces, and therefore we increase the amount of energy needed to either melt it or to boil it. If you were to look at the group 7 elements and their boiling points, this is a common exam question. In the group 7 elements, they go from fluorine to chlorine, this is boiling points, to bromine, to iodine, which at room temperature iodine is a solid, bromine is a liquid, and those two are gases. And the reason for the increase in boiling point is exactly the same. Whereas in fluorine F2 we have 2 times 9, so we will have 18 electrons. In chlorine we have 34, 2 times 17, we have 34 electrons, etc. So we have more electrons. Okay, and that stands for anything. If we think of polymers, if we think of polythene, which is made from ethene, which is a very low boiling point gas, but it's a huge big chains of ongoing monomers all joined together, and they end up with really high melting points, because for the very reason that there's huge numbers of electrons in these chains of monomers turned into polymers, maybe tens of thousands of monomers joined together. Okay, so that is the explanation of van der Waals. Now, in terms of melting point and boiling point, these things tend not to be soluble in water, because if we think about water, maybe we don't know that yet, although we should do. Okay, water is joined together by obviously covalent bonds, between the oxygen and the hydrogen. But when I dissolve something in water, I don't break those bonds. But water also has this very strong attraction between its molecules. Okay, and that attraction is a thing called a hydrogen bond. Now, if I want to dissolve something in water, I've got to get it in between these hydrogen bonds. Okay, between these water molecules. So therefore, I've got to break the existing hydrogen bonds in order to get my molecule between the water molecules. Now, if I took any of these here, chlorine, okay, the only intermolecular force, and this will become more evident as we go through this video, the only intermolecular force that chlorine can form are these van der Waals. Okay, and the attraction, even with a little delta positive and a little delta negative, that these have for our water molecules, okay, which have all got very strong delta positives and delta negatives the whole way through. I'll just draw those ones. The attraction that chlorine has for these is so weak, it is unable to break the existing hydrogen bonds, so simply cannot dissolve into water. Okay, well, not very well anyway. All right, so that is why things which can only form intermolecular forces don't dissolve in water. If I took a piece of polythene bag and I threw it into a bucket of water, I come back in many years and it'll still be there. Okay, so things with only van der Waals do not dissolve in water. All right, and tend to have pretty low melting and boiling points unless they have huge numbers of electrons, in which they then can have higher boiling points. Okay, right, so we'll look at the next one along, which was the permanent dipole attraction. Okay, so permanent dipole attraction. Now, a dipole, as you might imagine, as we sort of already spoke about, is a delta negative end and a delta positive end. So if I have a molecule and it has a delta negative and a delta positive, there is a dipole. Okay, two poles. And we're going to look at, first of all, we'll just look at temporary dipoles in van der Waals, and that temporary dipole means that the dipole was constantly being made and broken, coming and going all the time, but it was there to a constant level on all occasions. This time, the dipole is always there. It doesn't come and go like the van der Waals because the electrons are shifting around all the time. This one is there all the time. So look at how the molecule has to be set up in order to create this permanent dipole, as opposed to just plain old van der Waals forces. So we're looking at things which have a significant difference in their electronegativity. So electronegativity is going to be important in predicting, or differences in electronegativity are going to be important in predicting whether something has or has not got a permanent dipole in it. So if we think about electronegativity, and if we remember, the most electronegative element in the periodic table is fluorine, and it increases from the bottom left up to the top right at fluorine. So let's take something which is close to fluorine, just below it, and we take hydrogen chloride. Now, electronegativity is the attraction of a bonded pair of electrons, okay, to an atom, and chlorine is very electronegative. So if we think of these electrons here, in actual fact, they will sit much closer to the chlorine than they do to the hydrogen, because the chlorine is more electronegative than the hydrogen. And that is all the time. Okay, so what does that mean? Well, that means that the chlorine has an uneven share of the electrons and therefore is always delta negative, and this is always delta positive. Now that therefore means that you have now got a permanent dipole. Because of the differences in electronegativity, that dipole is always going to be there. So if I have another molecule of HCl, I will have the same, and if I have another molecule of HCl, they will always be the same. So unlike van der Waals, where the electron cloud is constantly fluctuating, and therefore so are the delta negative, delta positives, this one is not. These attractions are always there, or these dipoles are always there, and you have this permanent dipole attraction. And if we compared this, a molecule of this number of electrons with something similar size, but with only van der Waals, this would have a much higher melting and boiling point. Okay? Now, again, if we think about the solubility of these particular substances, again, if we remember, and I know we haven't covered hydrogen bonds, but you should have covered them in class. Okay, water is held together by these other intermolecular force, very strong hydrogen bonds. And in order for me to get something to dissolve in water, it's got to be able to form equally strong bonds with water, but these things can only form permanent dipole attractions, so therefore they are not able to form hydrogen bonds really, and many things which only have permanent dipoles will simply not dissolve in water. Okay, now HCl does dissolve in water, but for a different reason. Let's have a look at something else which would maybe have a permanent dipole in it. Okay, so if we look at, for example, let's take pH3. So the other thing that we have to be able to take into consideration here is the shape of this. So if we drew the shape of this, okay, it is that shape. So it's a trigonal pyramid, and my phosphorus is up around here. So it has got a delta negative, okay, and my H is H and H, delta positive, delta positive, delta positive. So therefore this will have permanent dipole. It has three polar bonds. It has one end of the molecule as being negative and one end of the molecule as being positive. Okay, so I can draw a negative end and a positive end. So it is a polar molecule, and that is permanently polar and can form permanent dipoles. Okay, so this would have a relatively high melting and boiling point. Right? Again, it still won't dissolve in water because it can't form hydrogen bonds with water. Okay. Right. So the next thing that we're going to look at then is a molecule which does have polar bonds. So we're going to look at CF4, and we're going to look at, we know that fluorine is the most electronegative of all elements. So that will be delta negative, delta negative, delta negative, delta negative. Okay, and our carbon will be very delta positive in the middle because the electrons are being attracted well away from it. But again, as I said in the last one, I can't now suddenly go, oh, that must have permanent dipole attractions. I need to look at the shape. So your understanding of shapes comes into play here as well. And let's draw the tetrahedral shape of this molecule. I haven't drawn a 3D. I'm assuming that you can all grasp the concept. So these are all delta negatives, and that's delta positive. So the first question we ask ourselves, well, does it have polar bonds? Well, yes, it does. It has, all of its bonds are indeed polar. Is it a polar molecule? And in order for it to attract another molecule like this, it's got to be polar. Well, no, it isn't, because no matter how I try to draw from one end to the other, it's always delta negative to delta negative. There's nowhere in this tetrahedron that I can draw from one end to the other that is delta positive and delta negative. Okay, so no matter where I draw my arrow, it's always delta negative, 2 delta negative. So this actually, despite having 4 polar bonds, is what we call a non-polar molecule. Now, if I was therefore to bring another CF4 into play here, and they came close to each other, would I get this permanent dipole-dipole attraction? Well, I hope you can see that we definitely would not, because the extremities of this molecule are all delta negative, and it's the same for this one. So what would they actually do to each other is they would repel each other. So even though this has 4 polar bonds, it's a non-polar molecule, okay? And the dipoles, if you like, cancel each other out. And these molecules will actually repel each other. So you need to be careful in terms of not just saying that something has got differences in electronegativity, therefore it has polar bonds, therefore it must be a polar molecule and have permanent dipole-dipole attractions. Polar bonds is not enough. It also has to have a shape, okay, which allows for dipole-dipole attraction. If I change the fluorine here, so if I change this to CHF3, so if I take this out and made this a hydrogen, which is much less electronegative, now suddenly I have a polar molecule, okay, because this bond here is non-polar. Alright, and I have a delta positive to delta negative end, and I will now have a polar molecule, and I'll have changed the properties of this particular molecule quite significantly. Okay, so we've covered very quickly, I know, but permanent dipole attraction. We're going to look now at the final one, which is the strongest of all if you're comparing like for like, so molecules with the similar numbers of electrons. Okay, so this is hydrogen bonds, and this only occurs when I have hydrogen, unsurprisingly, directly bonded to, it must be directly bonded to any of those 3. So NOF, nitrogen, oxygen, or fluorine. So for example, water was the one I spoke about earlier. So I have HOH, and I've just drawn the shape of it there. Okay, so this has hydrogen bonding in it. And it has hydrogen bonding because it has lone pairs on this atom. This is a very electronegative atom, so it's very delta negative, leaving these very delta positive. Now, it doesn't look at first glance much different than a permanent dipole from 2 polar bonds in a molecule. But what we have to consider is hydrogen is 1 proton and 1 electron. If its electron in this bond here is being dragged far away from the hydrogen, that leaves just 1 proton. So it's a really dense area of positive charge. That means its attraction to things which are delta negative is exceptionally strong. Down here around the oxygen, not only do we have very electronegative oxygen which pulls the electrons towards it, but we also have lone pairs of electrons which create a very significant area of dense negative charge. And that then, if there's something with a delta positive, will attract that very, very strongly. So when we get water, okay, we get a very strong attraction. That red line is a hydrogen bond. Okay, a very strong attraction between the delta negative oxygen, the lone pair on it, and the delta positive hydrogen. Okay, and the same occurs between other water molecules. And the beauty of water is it has the perfect hydrogen bonding structure in that it has 1, 2, 3, 4 possible hydrogen bonding regions, and other water molecules also have 4 hydrogen bonding regions. And that gives the perfect match-up and means that water, despite being a very, very tiny molecule with actually very few electrons, okay, so it only has 10 electrons, it's tiny, it has a boiling point of 100 degrees, which mightn't sound massively high, but if you compare it to similar sized molecules, it's exceptionally high, and that's because of this sort of perfect arrangement of hydrogen bonding where all water molecules can form 4 hydrogen bonds per water molecule. Okay, if we look at another couple that can form it, so we might look at NH3, okay, which is ammonia, and again NH3, delta negative, delta positive, delta positive, delta positive. So we have 4 possible bonding zones here, okay? But these ones can bond via with lone pairs of another ammonia. So, for example, like so. But each ammonia only has 1 lone pair on it, whereas there are 3 hydrogens here. So you don't get that perfect hydrogen bonding setup in ammonia that you get in water. These things can still dissolve in water though, because they can form hydrogen bonds. And remember earlier, we said that water was held together by, and we just said it again, was held together by hydrogen bonds. So these things have the ability to break the existing hydrogen bonds and make their way in between water molecules. Okay. Anything with hydrogen bonding in it also has really, really high boiling points. Okay, or melting points also. Okay, much higher than we would expect. So if I took a molecule like this, that's methanol, okay, and I compared that to a molecule of, let's say, ethane. Okay, so what's the only intermolecular force in ethane? Well, there's no differences in electronegativity of significance between the carbons and hydrogens, so that's only got van der Waals. Here we have an OH, this has hydrogen bonds. They have similar numbers of electrons. Okay, so we'd expect any van der Waals attractions to be similar, but the boiling point of these two is about 200 degrees of a difference. So it's a massive difference just by incorporating this little OH group. The other thing about this is this can only form van der Waals forces with water. So this is non-soluble. This, because of the presence of this group and can form hydrogen bonds with water, is very, very soluble, miscible with water. Okay? If I was to take another organic molecule, something like this, would that be soluble in water? Well, yes, it would, because you've got these groups here which allow hydrogen bonding to occur. This will also have a relatively high melting point. When you start making the carbon chain here longer and longer and longer, remember this carbon chain here is like this, it's non-polar. And eventually when you make that carbon chain too long, this molecule will no longer dissolve in water. Even though it can hydrogen bond at this end, this non-polar or hydrophobic part of the molecule prevents it dissolving in water anymore. Okay? Right, I'm going to have a look just at a little graph here, see if we can go through this and explain it. So we're going to look at just, this is just a boiling point graph of the hydrogen halides. Okay, and we frequently get asked to explain this. So HF has the highest, and hopefully you remember from just a minute ago that hydrogen is directly attached to fluorine, so it can form strong hydrogen bonds. HCl, okay, we should know, has got a permanent dipole, and I'll just write permanent permanent dipole attraction, because chlorine is much more electronegative than hydrogen, and you get that permanent dipole setup. But then how come these, because if we think of electronegativity from fluorine to chlorine to bromine to iodine, as we go down the group, the electronegativity decreases. So these will than the HCl. So how come they have higher boiling points then? Well, now we're into van der Waals, so we're not comparing molecules with the same numbers of electrons, because the bromine has got 35 electrons versus the chlorine has 17, so this has got increased van der Waals forces now. And again, the same reason is true here. We increase the van der Waals because iodine again has got 53 electrons, which is compared to the bromine 35. So as we go up here, we're increasing the van der Waals, even though this has got a permanent dipole or a stronger permanent dipole than any of those. Okay, so you just be aware of that sort of graph. Then, excuse me, if we were to look at, let's say, a molecule of methanol, a molecule of ethanol, and a molecule of propan-1-ol. So they've all got OH groups, so they've all got hydrogen bonding. But what happens here is we have CH3, C2H5, C3H7. So how would boiling point change here? Well, as I go from there to there to there, we would hopefully expect boiling point to increase. So the hydrogen bonding is the same, but we add more electrons. Okay, so as we go down, we've got more electrons, so we increase again the van der Waals forces. Alright, and that means that you end up with a higher boiling point as we go from there to there to there. If we looked at maybe a graph, if we go across a period, which is a frequent one, so we go across a period, we'll just label this sodium to magnesium to aluminium, and then we jump right away up to silicon, and then we come away down to phosphorus, up again, and then down again, and then we finish at argon. So again, this is melting point. So what's going on in this graph? There's a lot going on in this graph, obviously. So first thing we'll deal with these three. What's the bonding that we're breaking here? Well, this is metallic bonding, and it clearly increases from sodium to magnesium to aluminium. The question is why? Well, you go from +1 ion to +2 to +3. How many delocalized electrons do you have? Well, you have 1 electron delocalized here, 2 delocalized electrons, and 3 delocalized electrons. And a metallic bond is the attraction between the positive nucleus, +1, +2, +3, and the delocalized electrons. So as you go from there to there to there, that's exactly what happens. You get a stronger attraction. Silicon then has this massive jump. So how come suddenly silicon? Okay, well, silicon is just below carbon, and we should all know that carbon, diamond, and graphite is giant covalent. So it's the structure here, it's giant covalent. And if you remember what I said at the start of the video, giant covalent structures, if you're going to melt them, or melt them, you've got to break covalent bonds this time. So we're not dealing with simple covalent where we do intermolecular forces. And those covalent bonds are very, very strong, or even stronger if you go up a period into carbon. Then suddenly with this huge drop. And what's going on with this huge drop? Well, suddenly now we're into what we've been talking about for the majority of this video. We're into simple covalent structures now. Okay? Now they're all made up of the same elements, P4, S8, Cl2, so they have no difference in electronegativity. So what type of intermolecular forces will they all have? Well, they'll all have van der Waals forces. Okay? Now why is P4 down here? Probably should be a little bit higher actually. Up to S8, down to Cl2, and right down to AR. Well, it's to do with the number of electrons. Okay, so phosphorus has got, I'll try and write it in here, 60 electrons, 4 times 15. Sulfur has got 6. Sulfur has got a molecule of S8, so it has 128 electrons in there. So I'll just again 128 electrons. Chlorine has got 34 electrons, and argon is on its own there, it's monoatomic with 18 electrons. So this is reflecting that what we said earlier, that molecules with van der Waals forces have their melting and boiling point determined by the number of electrons. So phosphorus is sort of the second highest, sulfur is the highest, Chlorine is the second lowest and argon is the lowest, and that reflects the number of electrons in those non-polar molecules. So that's a very complicated, looks very complicated graph, but in actual fact it's pretty simple. And frequently you get asked, given the same graph, but for the period above, the period of lithium going across to neon, and the reasoning for the trends is exactly the same. Okay, right guys, I think I've covered pretty much the basics of intermolecular forces and got in a reasonable amount of depth. So hopefully you're able to take a molecule, take a structure, and decide whether it has van der Waals, permanent dipole, or it can hydrogen bond, and then you're able to take information and explain based on the intermolecular forces that are present whether it will have a high or low melting or boiling point, and whether it will or will not be soluble in water. Okay, so hopefully that helps, and good luck.